Swayam Prabha. Digital India. Educated India.
Today we will be discussing about robot programming, and in the last class we briefly looked at accuracy, repeatability and resolution, and today we will start off with robot programming. Now robot programming is essentially a facility given by the robot manufacturers to enable the users to very easily write a program and then execute the program on the robot. Now you would understand that essentially if the manufacturers did not give this user interface, then what the person buying a robot would have to do is he would have to write his control algorithms, write in the assembly language, and then learn a lot of robotics theory and control systems theory to be able to use a robot. So in that case nobody would be buying a robot. And because of which the robot manufacturers are essentially giving a very simple interface. Sometimes it is a very simple language, sometimes it is a GUI based interface, and today we even have pointers where you can use the mouse on the computer and move the robot, and the software would automatically generate a program which is going to run the robot. So today we will look at a very simple the most general way of programming a robot. Okay, in the last couple of classes what we saw is the question of evolution of NC machines, robots, and as NC machines and robots evolved, we also had the evolution of the computer programming languages, and some of these robot languages are based on the computer programming languages, for example BASIC, Fortran and Pascal. And so if you look at this here, so we saw that about 1950s with the invention of the microprocessor, essentially we had the evolution of the NC machines. And after the evolution of the NC machines, we had the evolution of robotics, and essentially NC technology, or what we call by NC as numerical control. So NC basically means numerical control or control by numbers, is the same as that for a robot, and since 1950s NC machines have evolved in this way. So first in the early days we had one program which was controlling one machine. And this machine basically, I mean it is a computer basically plus a machine tool which is this one. So in the early days basically we had one program which is basically being run on a computer, on one computer, and that is controlling one machine. Now this machine can be a lathe machine, it can be a milling machine or whatever machine. Now as the computer got more powerful, what happened is we had one computer controlling many machines. So here you see that there is one computer which is connected to different machines, and the computer is controlling different machines. Now as the computer became more and more powerful, so this is about 1960s, as the computers started becoming more and more powerful, this is about 1980s, we had what we call flexible manufacturing, and we have one computer. So we can say one computer here which is controlling many machines. So this computer is controlling a parts carousel, it is controlling a robot, it is controlling a machine tool here, and it is controlling another machine tool there. So essentially it is one computer which is controlling different kinds of machines. Now what you see here is that this computer is able to control different machines, means it is also being able to communicate with different machines. So this is where we also have to talk about the concept of communication. So by communication I mean machine to machine communication. How do machines communicate or talk to each other? Now as we progress, so we see early NC machines about 1950s, then we have computer numerical control, CNC. So this is NC, CNC, then we have FMS which is called flexible manufacturing systems, and then further as the computer became more and more powerful about 1990s, we have what we call computer integrated manufacturing. So this is essentially the computer controlling all other functions of the not only manufacturing, so it controls manufacturing, then it controls materials resource planning. Okay, so materials resource planning, manufacturing, then scheduling, okay, then inspection, etc. So here we see that as the computer has become so powerful about 1990s, that the computer is able to control several of the industrial applications such as manufacturing, materials resource planning, then scheduling, inspection, etc., etc. And this is what we call by the computer integrated manufacturing or SIM. Now Now moving on to robotics essentially. So, the robot essentially consists of the mechanical hardware, which consists of the arms. So, the robot would have arms. So, this is my robot links, or let us say this is my robotic arm. So, it would be basically the arms, which are mechanical rigid link systems connected by joints. There is some motion transmission. So, from the motor, it is the motion is being transmitted to the joint by means of gears or belts or pulleys, and then at the end effector we have a gripper. So, the mechanical hardware part essentially consists of the arms, the motion control units, and the gripper at the end. So, this is one unit. The second unit is the robot control unit. So, the robot control unit essentially consists of the robot controller. So, the robot controller is the one that is actually controlling the robot. Okay. When I mean by controller, basically I mean the PD or the PID controller, which is actually controlling the joints of the robot. Then we have actuators, which are motors. Then we have for feedback closed loop control, we have sensors. Then we have power amplifiers, and then we have analog to digital converters and digital to analog converters. Okay. So, ADC and DSCs are essentially for, this is for taking in signal, analog signal will be coming inside, and this is for digital to analog conversion, which is the machine giving a digital signal output. Now, why are these ADCs and DSCs required? So, these are required for some kind of communication. Okay. So, when for example, the robot is assembling two parts or is touching or is pushing an object, then if you want to control the force with which the robot is pushing an object, in that case I need to read the force sensor. Now, the force sensor is being read by an analog to digital converter. So, the analog force signal is being converted to digital, and then that is being read in the computer memory, and some action is being taken. So, as we go along we will see how this functions, what are the commands. So, basically this is for communication. Now, this is the second part, the robot control unit, and the robot third part is the central controller for interfacing robot with other machines. So, this is my central controller which is going to interface the robot with other machines. Now, a robot will not be working in isolation, it will be working with other robots or it will be working with other machines. So, this is very important that there should be some kind of interfacing. Now, this interfacing again means that there is some kind of communication here. So, this interfacing also means there is some kind of communication. So, we will also look at how machines communicate with one another as we go along. So, the total system consists of the mechanical hardware, it consists of the robot control unit, and it consists of the central controller, which is interfacing all the machines for communication. Now, there are two ways by which we can program a robot. So, using a robot or programming a robot, we can program it using a teach pendant. So, a teach pendant is something like a remote control of the TV, where the number of joints are marked 1, 2, 3, 4, 5, 6 like that, and there is arrows which are indicating clockwise and anti-clockwise motion. So, this is something like a joystick. Okay. So, let me draw it again. So, there is just to give an example, this is a joint number, and there would be arrows with a joystick like this, and there would be a toggle switch here. Okay. So, by toggling the switch in the clockwise or the anti-clockwise direction, you can move the corresponding joint. So, for example, if I take the joint number 1 and I toggle it on the right, it will move clockwise. If I toggle it on the left, it will move anti-clockwise. And by doing this, what we can do is we can take the robot to different positions in space. So, here just to give a very brief example here. So, we have an object which is kept on a table. Okay. So, what I want to do is I want to pick up this object. So, you would understand by now that essentially if I want to pick up this object, I need to know the CG of this object. Now, in space, to find the coordinates, the position and orientation of an object is extremely difficult. Okay. So, if I were to find out what is the position orientation of this object, I will not be, it will be very difficult to find it out. So, one way is use a teach pendant and toggle each of the joints. So, I slowly move joint number 1, joint number 2, joint number 3, and slowly I bring it this way to I bring it till here to catch the object. So, this I do by using my teach pendant, and when what happens here is when we are moving the teach pendant, what is happening is the position and orientation. So, position and orientation coordinates of the robot is being displayed. So, when I am moving the robot in space using the teach pendant, I can also see what is the position orientation of these points as it is moving, position orientation of the end effector. So, essentially here what we can see is that if I do not know the coordinates of a point, then I can use the teach pendant, take the robot to that location, catch it, and take it out and go and drop it somewhere or do some other task. And whatever position it is moving through in space is being recorded in the memory. So, I can then play back that point. Okay. So, teach pendant is basically used to manually teach. So, manually we are using the teach pendant to take it to different points that are recorded in the robot's memory, okay, and then these points can then be played back. So, for example, pick and place application, we use the robot to pick up something and then to keep it somewhere, and at every location the position orientation is being recorded, and then we can play back the task. Okay. Now, this is not normally done in industrial applications, because in industrial applications we require the robot to move from one point to another point extremely fast. So, it should be, the robot should be taking a trajectory or should be performing a task in the shortest possible time. So, this would mean that if you teach it, it would probably take more time, because the trajectories need not be optimized. So, what is done in industrial applications is normally we write a program to perform a task. So, a program based control is essentially like normal language. You want to perform a task, perform a function using C language or Fortran, where we write a program and then the program executes line by line, and the task is done. So, here we write a program. So, a program essentially is a sequence of motions in a language, and in robotics we normally use the VAL language, which is called Victor's assembly language, to write a program. Now, in the robot based programming we used a program such as VAL to perform the task. In this case I am using a teach pendant to perform the task. Now, this is used, teach pendant is used essentially to find coordinates in space. So, coordinates in space, because if you do not know the coordinate, then the only way you can find the coordinate is to use the teach pendant, take the robot there, and then okay, this is one application where it is used. The other application where it is used is essentially where we need human skills. Okay. So, tasks requiring human skills, for example, welding. Okay. So, welding is an application which is extremely difficult to perform for a robot. Why? It is very difficult to exactly get the positions in space of how an expert welder actually performs a welding task. So, in this case what is done, an expert welder actually takes the welding torch, moves it in space, and those points are recorded, and we can play that back. So, that can be done by using a teach pendant. So, these are two ways we will see as we go along. So, the first is teach pendant based, the second is program based control. Now, as the computer has become more and more powerful, the whole computer system has evolved. Machines have also evolved, NC machines have evolved, robots have evolved, and along with this evolution the programming languages have evolved. Okay. So, there has been three generations of programming languages. The first generation is consisting of languages which could perform very simple commands, say for example, just pick and place applications with very limited interaction with the environment. So, first generation languages were early languages, say it was from 1950s to 1970s maybe, very simple languages for the robot just to pick and place objects without any interaction with the environment. So, we could not have things like force torque sensors, we could not have ADCs, because there was no means of communication. The second generation language is about 1970s onwards. So, 1970s to 1990s okay, is my second generation of languages, and the second generation of languages, the difference with the first generation is that these fellows could interact with the environment. So, second generation robots could interact with the environment by means of force sensors, touch sensors, ADCs, DSCs, vision, maybe vision, etc., etc. And the fundamental difference being they were able to have sensor input output. Okay. And this is what we call the second generation languages, and the third generation languages is still continuing, and these languages are what we call intelligent. These languages have some kind of intelligence, or they have the intelligence capability to understand general commands. What we mean is general human commands. So, we can say general human commands to perform a task. For example, if I am going to pick up an object and keep it somewhere. Okay. So, the first generation, second generation language will essentially mean that you define the points of the object in space, then tell the robot to go there, open the gripper, close the gripper, catch the object, pick it up and place it somewhere. Okay. But in a third generation or intelligent language, it would be something, a language which would be human, like the language we use in our daily use. For example, if you tell the robot to pick up an object and keep it somewhere, it should be able to understand. that what is the meaning of pick up and keep, and it should be able to automatically generate the language. Now, that still is a distant call, essentially because human language is very very difficult to interpret in terms of the context, okay, and the meaning. For example, a human being could say different things, but mean the same thing, or say different things and not mean anything. So, and the context in which what is being said. So, that is the reason why this intelligent language for a machine to understand a human being and perform a task is extremely difficult even as of today. So, there are 3 generations of languages: first generation, second generation, third generation, and these are examples of some languages which were developed in the early days. So, Victor's assembly language is the one most commonly used. It was developed in 1960 and developed by the Unimation Corporation for the Puma robot. So, the Puma robot was one of the earliest robots, and it used VAL language. So, this is VAL, this is what we call by VAL, and today about 95% robots would be using some derivative of VAL language only. The other language that was used, that was so this is about say 95% robots even today use VAL, and this we have had some evolutions of VAL. We have had VAL 1, then we had VAL 2. The basic difference between VAL 1 and VAL 2 is that in VAL 2 you had sensory interface. VAL 1 did not have that much of sensory interface. The other language that was used was that was developed was AML. So, this was developed by IBM for manufacturing automation about 1960s again, and today IBM does not make robots anymore. So, this language is not used, it is rarely used. The other language was RPL. So, this is also about 1960s, and it is a Fortran based language. It was developed by other robotics companies. Now, these companies are no more there. So, this AML and RPL are no more there. So, today the majority of the robot manufacturers use some derivative of this language, which is called VAL. So, here we will be studying about VAL language. We will see how to write a program in VAL language, then we will go to the lab and we will see actual application of a robot, of a Puma robot in using VAL language. So, the basic, now something to remember here is that the Victor's assembly language, the base language of that is BASIC. Okay. So, you might have studied what is basic language, and basic language is one of the earliest and the simplest way of writing a program. And how we write a program in basic language is we have a line number, say for example, we have a line number, then we have a command, then we have another line number, then we have another command, and this is the way we write a basic language. So, the structure of VAL language is very similar to the basic language, and the basic commands in VAL 2 language consists of these 4 parts, or this is the structure. Let's talk about it as of program. So, the structure of the program would look something like this. First, when we start writing the program, we have to define the constants, we have to define the variables, and we have to define the data objects. Now, what are constants? Constants are, for example, values of pi, say pi is equal to 3.14. Then we can define the value of pi as a constant, that pi is equal to a constant some number. Next is variables. Now, variables can have a combination of letters plus numbers. Okay. So, for example, a variable name, a point, let us call it point 1 is a variable. So, the variable name is point 1. So, that can be made up of a combination of letters and numbers, okay, up to 8 characters are called variables. Now, in robotics we have to move from point to point, which will mean that these variables are essentially points in space, okay. And then data objects, so something similar to your C language, this you can define a structure. Okay. So, these 3 are defined at the very beginning of a program. Second is the second part of the program would consist of motion control commands. Now, motion control commands would basically mean to move the arm, move the end effector or arm to perform a task. Okay. So, a robot moves in space, we know, to do a task. So, to move the robot end effector or the arm around, we normally use our motion control commands. Then the third part of the program is the robot hand control. So, the robot is going to do a task, it has a gripper. So, the hand control command would be, for example, open the gripper, close the gripper. So, the third part would be hand control command. And the fourth part, which we talked about today, is that the robot has to interact with other machines. So, there has to be some kind of program control, that means some kind of logic, Okay. In the program there has to be some kind of logic. For example, pick up this object first, do this, then pick up this object, do that. Okay. So, some kind of logic has to be there in the program. Again, if we are using some kind of input output, for example, we are using a force sensor and we want to measure the force at being applied at some point. So, we can write a logic statement that if the force exceeds say 10 Newton, then exit the loop, do something else. So, this is so it needs logic and it also needs some kind of input output. Now, input output is basically for communication. So, communication plus sensor input output. Okay. So, so the fourth part of the program consists of the program control, which is the logic at which the program is following, and then some input output statements which are used for communication with other machines or with sensor input output. So, when we write a program, we should ensure that we are writing it in this sequence. First are constants, variables, second is motion control commands, third is robot hand control, and fourth is program control and input output control. So, first let us start off with the first part, which is constants, variables. Now, variables we have said can consist of names, okay, made up of letters and numbers up to 8 characters. So, this is defining a point, and this name of the point is P1. Now, how this point P1 is defined in space is the first 3 characters there, sorry, the first 3 units there are x, y and z coordinates. The last 3 are the angles, the alpha, the theta, alpha and gamma angles that the end effector makes with the last axis. So, if I were to write here, this is my, so it is here, okay, this is my 0 0 0. So, the end effector here point or if I want to go to any other point in space, or let's say this is my point P1. Okay. So, it essentially means that at this point P1, the coordinates of that point is 3, 4 and 5 with respect to the base, and it is making an axis, this fellow is making an angle. So, there is an x, y and z coordinate there. So, this is my z, x and y. Okay. So, there is a coordinate system which is put there. So, the angle that it is making with the, this axis is making with the base reference frame. So, there is x, y and z here. Okay. Sorry, this is my z axis, this is my x axis, x0, z0 axis. So, the axis, the angle that this makes with this one is what is my last 3 coordinates, which is given theta, alpha and gamma. Okay. So, for any point, suppose I want to take the end effector from this point to this point, okay, then at this point I have to give my x, y, z plus I have to give my angle of theta, alpha and gamma, saying that when the end effector reaches this point, what should be the angle of the end effector with respect to the base frame. So, this basically has 6 parameters. The first 3 are x, y, z, the second are alpha, theta, alpha and gamma. Now, if I do not specify this, then it basically means that this is 0 0 0 or we are not interested. Okay. So, you can only give this 3 or you can give all the 6. So, we can give just 3 or we can give 6. Now, this defines a point in space. Now, once we have defined a point in space, for example, I have defined my point P1 at some point and I want to move to P1, then I should be able to move to that point, and the command for moving the end effector to that point is essentially move P1, and so this is going to take me to my, so move P1 essentially takes the robot end effector to the point P1. P1 has already been taught here. Okay. Now, let us look at this example. I am here, I want to go to this point P1. P1 is already taught, the coordinates of the point have been given in the earlier case as here. So, we know what is the coordinates of the point P1. Now, I want to go from here to here. Now, the question that would come up here in everybody's mind would be that what are the different ways by which the end effector can go from here to here. Okay. So, how many paths are possible, or how many paths are there to go to point P1. Okay. So, if you were to try to answer this question, then we will know that what is the answer to this. Now, it can go in almost infinite parts, it can go in a straight line, it can go like this, it can go like this, okay. It can even go from here like this and go to that point. So, all these points, all these paths or trajectories are possible. Okay. So, we can say path or we can say trajectory here. So, so how many paths would be possible? We see that this is infinite. Okay, infinite number of paths are possible. So, the question comes that when it is going from one point to another point, which path it should take. Now, immediately if you think about it or try to answer this question, what would come to your mind is that maybe it should go straight like that. Okay. Why? Because it is the shortest distance, but unfortunately that is not correct, because what is important here is that it should take a path where the energy required, okay, should be minimum. So, it should take a path, which path? Energy optimal path, energy efficient path should be taken, and this energy efficient path need not necessarily be a straight line. Okay. So, most of the cases you will find that the straight line is actually not energy efficient. Why? Because if you want to move in a straight line, what is the meaning of a straight line? A straight line means that there are infinite points here. Now, at each of those points, what the robot will have to do? It will have to do inverse kinematics at each of these points, find out the corresponding joint angles, and then go to the enforce those joint angles. So, that first of all is going to take a lot of time, because it is doing inverse kinematics, and second of all, to follow exactly these points, it will have to slow down the system. So, the system will become extremely slow if it has to follow a straight line. So, in general, straight lines are not followed. So, please be careful here that whenever we say go from one point to another point, it does not mean that you should go in a straight line. So, the question that comes up here is, if you are not going in a straight line, then which path should you take? And the answer essentially is that you should take an energy optimal path, or the path which will take the least energy. So, path energy efficient path, which means least energy path. Okay. Now, how do you get the least energy path? One way of finding the least energy path is that when it is moving from this point to this point, we are going to move the least number of joints. Okay. So, if I move the least number of joints, for example, if I only move this one from here to here and it is able to take this path and come here, then it is going to be taking lesser energy than moving all the joints together. Right? I hope that point is clear. So, when we are trying to find a least energy path, one way of trying to find it is by using the moving the least number of actuators. So, a very important result here is that something to note about is that move least joints to get energy efficient path. Okay. So, essentially if you are moving the least number of joints, in this particular case, for example, if I am moving only this one, what would happen is this will take a curve, and then we will get to point P1 and the energy required will be less. But something to note, if you are moving the least number of joints, this trajectory here will not be a straight line, it is going to be a curve, some other curve. Okay. So, what we see here is that there is one command to move from one point to another point, which is the move command, and we can move to the point P1 simply by saying move P1. This fellow will not probably move in a straight line. So, this is not a straight line. Okay. And we also know the reason why it is not a straight line, because it has to be energy efficient. Now, there are some applications in robotics, or many applications in robotics, where we are required to move in a straight line. For example, when you are inserting, so for example, in electronic assembly. So, in case of electronic assembly, you know that the chips, okay, the computer chips, they have very thin legs. Okay. So, you know that. Now, if you want to insert this into the motherboard, okay, then what this is this is a computer chip, and these are very thin legs. Now, if you have to insert it, there are holes in there, and it has to be inserted exactly in a straight line. Okay. So, all electronic assembly today is done by using robots, whether it is for computers or it is for mobile phones or cameras or whatever. All electronic assembly is done by robots, and electronic assembly basically means you have a motherboard and in which you insert chips at different places. Now, this chip insertion has to be done in a straight line. Okay. Why in a straight line? Because you can see that the legs are very thin and they are straight. So, when we are inserting, the motion has to be in a straight line. So, this is a requirement of a straight line motion now. Okay. So, there is also a requirement of straight line motion. So, if you want to move in a straight line, for example, during electronic assembly, then we use the command S. So, this command basically means move in a straight line, move in a straight line. Okay. So, there are two commands, move and moves. The move command essentially means move to the point P1, moves means move to the point P1, but in a straight line, and this is normally used for assembly, for pick and place, pick and place. So, similarly for pick and place, when a robot is picking up an object, for example, a robot is, so we have an object here, let us say we have an object like this on the table, and I want to pick up this object. Now, for a human, if you are going to pick up, what we essentially see is that I go from the side and I pick it up. Why? Because human beings have eyes and we can see where it is. But if but when you are asking a robot to pick it up, the robot cannot, robot does not have eyes. So, essentially what we try and do is we keep it safe, and what is the safe path is I am going to go from the top, catch it like this. So, I will first position my hand on top, then go down like this, catch it and lift it up like this. Okay. Because for example, if I give the coordinate of the point and I ask the robot to go here, it can take any trajectory, that is what we have seen. So, it can go from here, it can go from here, it can even try and go from the bottom. So, what will happen is there will be an accident. So, to avoid that, in case of robotics, what we do, we always go to the top, then move in a straight line down and then move up in a straight line again. Now, here we move in a straight line, because if I give my move command, if I were not to move in a straight line, what can again happen is the robot can take any other trajectory. So, in that case there is a chance of a problem again. So, we always ensure that this motion coming down and going up is always in a straight line. So, the application of this command, this moves command, is basically for moving in a straight line, for assembly, electronic assembly, for pick and place applications where we use moves. There is another command which is called draw. Now, this draw command is an incremental command. So, incremental basically means that if you want to make a change to the previous command, for example, I have said move to the point P1, but I have not got exactly to the point P1 and I want to make some changes on that now. So, then what I can say is, after saying move to P1, I can say draw, and this moves in the x direction, y direction and z direction. Okay. So, whatever this is incremental. So, wherever it has reached, for example, the robot has come to this point, just for an example, okay, but I wanted it to come to this point. Okay. So, what I will say is that it has reached this point, but now I want it to come to this point. So, I want to change little bit of the coordinate here in this direction, okay, x, y and z directions with respect to this. So, this is my x, y and z. So, this change I can make by simply saying, so let us call it del x, del y and del z. Okay. So, this is an incremental change from the last position, and these are very small units of motion in the x, y and z directions correspondingly. So, draw is basically used to make a correction on a command. Approach basically means approach the point P1 and keep a distance of 50. This is basically used for picking up. Okay. So, as I just said that when we are picking up an object, you have to go from the top. Why? Because otherwise there is a chance of an accident. So, whenever we pick up an object, so I have an object here now on the table, let us say this is my object I have kept on the table, I want to pick it up. So, what would happen is I will keep my robot end till here. So, this is my approach. So, this is the point P1, okay, which CG of the object which I want to catch. So, what we will do here is, first if I say approach P1, this robot will go in this is my z direction. So, in the z direction it will keep from P1 it is going to keep a distance of 50. Okay. So, P1 approach P1 50 means from the point P1 it will go and position just on top of the point P1 and keep a distance of 50 from that. If we say depart, okay, depart means after catching it, it is again going to go up this way and stop on top and keep a distance of 50. Okay. So, approach and depart, this is basically used for picking up objects, Okay. So, approach is approaching an object, catch it and then go back. Depart is after catching you go back. So, approach S and depart S again means it means more or less the same. Approach S is approach in a straight line, and it is similar to approach and depart. So, this is the variables and motion control commands. So, we have first you have to define the point, then we need to define the move commands. We have to use the move commands to move the point around in space, or move the arm around in space. Then approach and depart is before we catch an object. So, this brings us, this is the first, we looked at the constants variables, then we looked at the motion control commands. So, the third what we need to look at is the hand control commands. Now, the hand control commands are essentially open and close. Now, this is easy to understand that there is a gripper here and the gripper has 2 fingers. So, this is open and this is my close. After catching an object, suppose there is an object here, it has caught an object, it has to close now. So, this is my close. So, this is open and this is close. Okay. So, this is the two commands of open and close. Now, open and close essentially are used for catching an object. Now, there is something important here which we should keep in mind, is that suppose I have an object on the table like this. Okay, this is a table and I have kept an object, and this is my object on the table. I want to go and catch it. So, what suppose I write a program like and I want to go and catch it. So, what we will do is, this is my gripper, this is my point P1, this is my point P2. Okay. Now, suppose I write a program like this, which I want to pick up this object P2, I want to pick up this object which is CG at P2. Suppose I write a program like this, that approach P150, sorry, approach P2, or let's write it this way, move P1. Okay. So, I have already defined the point P1. So, the robot comes here to point P1, and I define also the angles correctly, so that the end effector comes exactly like that. Then I say open. Okay. So, the robot opens the end effector. Then I say moves P2. Okay. Then I say close. Okay. So, it catches the object. So, it comes here. Okay. Then it catches the object. So, I say close, and then I again say moves P2. Okay. So, suppose I write a very simple program just to catch this object which is kept on a table. Now, if you look at the logic of this, it appears that the logic is correct, but there is a little problem here. If you think a little deeply, what you can see is that this program is likely to have issues, or there is a chance of an accident here. Why? Because we say move, let us follow this, let us put a line number 10, 20, 30, 40 and 50. Okay. So, the first line says move to P1. Okay. So, move P1 means this is my point P1, and the robot comes and stops like this. Okay. P1 is already defined, the position x, y, z, and the angles theta, alpha and gamma are defined, so that it comes like this. Okay. Next I say open, so the end effector opens. Okay. And then I say moves P2, so the end effector comes down like that. Okay. Now, what is going to happen is this will execute first. So, this will execute first. Okay. Then after this line is executed, this line will be executed. Okay. Then it will execute this line. Now, the moment it executes this line, what is the execution of a line in terms of when we talk about a program? So, as long so here basically what we mean by execution of a line is, what the compiler will do is it will issue a command of open to the gripper controller. Okay. So, what does execution of this line open mean? It essentially means that the compiler understands that this line is open. So, it will tell the gripper controller to open, and then it will immediately move back to the next line. Okay. So, first we will execute this line, then we will execute this line. The gripper controller is being told to open, okay, and then immediately it will move to this line. So, it will start moving to point P2. Now, what can happen here is the gripper controller, the gripper here will take some time to open, right. So, this is a physical system, the gripper is a physical system. So, basically when the gripper is here, so what it basically means is that in this line the gripper comes and positions here. Second line is open command, and open command the compiler tells the gripper controller to open, the gripper controller opens, and then immediately it moves to the third line. Why? Because once this is executed, it moves here, and as the gripper controller is opening, because it is taking some time, the robot is already moving, okay, in the third, because it has come to this line now. So, this fellow, as it is opening, it is also moving, right. So, what can happen is if it is not fully open, it is going to hit this object now. Okay. Now, the third line, so it has come to moves P2. So, the object has moved to, so the gripper has moved to this position of moves P2. Now, what we can see is after this line is executed, it is immediately going to go to this line, which means it is going to say close. Now, this one again the same problem will come, that this will go to the gripper controller. Okay. Now, the gripper controller will take some time to close. Okay. But as far as the program is considered, the moment this line is executed, it will move to the next line. So, when the gripper is closing, the robot is again moving. Okay. So, what would happen is if the object is not completely caught, the gripper has moved, the object is going to fall out of the gripper now. Okay. So, this is a very simple example to show that this command, especially open and close, takes some amount of time, and because of this time we have to be very careful when we are using it. Okay. And we have to be very careful because the object, if the gripper is not fully open, it can hit the object, and when it is catching, if it is not fully closed, the object can fall off. Now, so this basically means that this command open and close here are open loop commands. So, these are open loop commands, meaning that the robot will immediately go to the next line without ensuring whether it has fully opened or it is fully closed. So, if you want this to be a closed loop command, then what we have to do is we have to use the command open immediate and close immediate. Now, this two commands OPENI and CLOSEI are closed loop commands, which means that in terms of the program that is being executed after the OPENI, suppose I say OPENI here, it basically means that the next line will be executed only after completion of this line. Okay. So, the meaning of closed loop here is next line Okay. So, this is the meaning of closed loop command. So, when we are basically trying to catch an object, okay, and using the open and close commands, then we use the closed loop commands, which are OPENI and CLOSEI. Now, so here it should be OPENI and CLOSEI, because these are all closed loop commands. Okay. Now, there is another command which is called CLOSEI 75 in VAL language, which means that if you can control the opening here, suppose if you can control the distance between this two fingers, then we can you say CLOSEI 75 in VAL, which means that this is 75. So, the fingers will close until the distance is 75. Okay. So, this is something important to note, that when to use open and when to use closed. When we are moving to catch an object, then we are going to use OPENI and CLOSEI. Now, if it is just moving in free space, okay. So, if the end effector is moving in free space and is not catching something, then we can use open and close. Now, how would that help? This is much faster. Okay. This is not a closed loop command, it is an open loop command. So, as far as the compiler and the program is considered, this is much faster. This command is much faster, but we have to be careful that when we are using, we are trying to catch an object, we have to use OPENI or CLOSEI. So, this is the third part of our program. Robot hand control. So, we have seen variables, constants and data objects, we have seen motion control commands, we have looked at robot hand control, and the third what we are looking at now is we are going to see program control and input output control. Now, program control would mean other parameters which require to be controlled. So, this is the speed at which the robot is operating, and this would basically mean 60 inches per second. This is the FPS unit, and we can also say 60 meters per second. 60 meters MPS. So, 60 meters is very or 60 millimeters per second, okay, or we can say percentage of max speed. Okay. So, this is how the speed of the robot for a particular operation is defined. We can also define a path and say the path has to go through these points A1, A2, A3. So, this is my A1, A2, A3. So, this is A1, A2 and A3. So, it will take a path which will go through these 3 points. Okay. Now, we can say pause, this is for pausing. Pause is similar to a delay in a program. So, it will keep it delayed there for some time. Now, let us look at a very simple application where this robot is expected to pick up an object from here, okay, pick up this part and then keep it here, and then pick up another one from there, keep it here, keep it here, keep it here, in that order. Okay. Okay. So, the task here is pick from the conveyor and place on the table. Now, what is required here is now it becomes very clear that apart from your move, what we need to know is we need to know the coordinates of these points. Okay. So, we need to know coordinates. So, coordinates of points. Okay. So, for example, I need to know the coordinate of the pick point P1, I need to know the coordinate of that drop point P2. Okay. So, these coordinates I need to know. The second thing is there has to be some kind of communication. Okay. Communication between the conveyor and the robot. So, when the part has come, the conveyor should be able to tell the robot that the part has come, you go and pick it up now. So, there has to be some kind of communication between the conveyor and the robot. So, there has to be some kind of communication here. Okay. Now, suppose the part has come, it has to be sensed. So, how will the conveyor sense? So, there has to be some kind of sensor here. So, I just give an example of a sensor here, and let us say there is a sensor here. Okay. Something like a inductive sensor or a proximity sensor, which is sensing that a part has come. So, after the part has come, the conveyor will stop and will inform the robot that the part has come. Okay. So, maybe it will do it using some channel line, channel number 1, let us say. Now, once the robot receives this information that the part has come, now it has to activate the program, pick it up, okay, pick it up and then keep it here. Okay. So, take it from there and put it here. Okay. So, the robot understands that the part has come, it picks it up and then keeps it here now. Now, after the robot picks it up, the robot has to again inform the conveyor that the part has been picked up. So, it has to have some channel line by which it will inform the conveyor that the part has been picked up. So, now the conveyor can start moving again. Okay. So, this essentially shows us that there has to be some kind of communication between the machines. Okay. So, this is the first point that we are seeing. The second point is the communication part. Now, the third part is there has to be some kind of logic. Okay. What is this logic? The logic is that first it is going to put the part here, then it will put the part here, then it will put the part here, then it will put here. So, it is doing some kind of indexing. Okay. So, the program must consist of must contain all these parts. First of all, the coordinates of the points where it has to pick up, there has to be some communication between the machines, and there has to be some logic for indexing the various or for indexing to the various points in this palette. Okay. So, next thing that we will look at is how to index, how to use this logic, okay, what kind of logic is used, and then how to communicate. This is another example, robot center cells, and this is an example where there is a conveyor and there is a part which is coming. So, we have some kind of sensor. So, the sensor must have some kind of communication with the robot there. It must be able to tell the robot that the part has come, and after the robot has picked it up, it should again tell the conveyor that the part has been picked up. So, you proceed. Now, the robot can go and put the part here, can put the part here, or can put the part here. Okay. So, as the part is coming, the robot is picking up and keeping it there, keeping it there and keeping it there, right. But now, if you see there is a problem here, that suppose 3 parts have come and the robot has put it here, here and here. Now, the 4th part has come and the robot picks it up. Now, what would happen is what we call as deadlock, which basically means that the robot has picked up a part. Now, it cannot remove any of these parts because it is already holding a part, and now it cannot do anything and the whole system is deadlocked. So, in the program sequence, the sequencing in the program is very, very important, and the sequencing should not lead to any kind of deadlock. Okay. So, one example of deadlock was explained here, that the robot has picked up a part and these machines are all engaged now. So, now the robot cannot do anything, right, it is completely deadlocked. So, the sequencing is another aspect in a program that we have to be careful of, apart from the logic and the communication part. Now, how do machines communicate? At the very simple level, machines communicate by on-off signals. Okay. So, how do machines communicate? Okay. So, at the simplest level, simply by on-off signals, by making some channel low and making some channel high. Now, what is the meaning of high and low? So, it basically means this is high and this is low. Okay. So, suppose we have 2 machines. We have a robot and we have a conveyor. So, we have a robot here and we have a conveyor, and this is communicating with each other. So, essentially what we can say, there is line number 1 and line number 2. Okay. Line number 2 is, you can say, it is a wire or a channel with a number 1 or a number 2. So, the robot, once the part has come, the conveyor can make channel number 1 high. That means it can make it 5 volts, and the robot will be measuring this 5 volts on channel number 1. The moment it becomes high, it knows the part has come. So, at the lowest level, this communication is simply by means of on off kind of signals, and this on off basically means 5 volts or 0 volts okay, on particular channels. Now, these are some of the program control commands. Okay. For example, go to. So, this means go to line number. Say for example, a program is being executed and you want it to go to some other line okay, for logical reason. So, here we can say go to line number. So, this is go to line number. Then we can have go sub return. So, this is a subroutine. So, this is a sub which is being used. For example, in this example that we saw, we are indexing. Okay. So, we can use this indexing as a subroutine or a sub function. So, this is a subroutine. Okay. So, indexing subroutine is there. So, after the robot picks up, it simply goes to the indexing subroutine, indexes it, puts it here, comes back. Then again it picks up a part, it again indexes it, goes there. So, this indexing is done by the subroutine which is used for indexing, not in part of the main program. And the basic structure is go subroutine and then return. Okay. Then we have if then else statements. So, if some relation is true, then do something else, do something else. For example, if force being applied is greater than 1, then continue, then stop, else continue pushing. Okay. So, these are if then else statements. Then pause and proceed we have seen. Okay. Now, how this on off signals are being used is by using this the command which is called signal. So, signal basically means signal is signal SIG is sig standing for signal. Then we have a line number or a channel number, and then it is high or low. Okay. So, the basic structure is high or low. So, low means 0 volts, high means 5 volts. Okay. So, the basic structure that we are seeing here or we are seeing here is so this is the structure. Okay. Signal stands for sig stands for signal, then channel number. So, 2 is the channel number 2, and plus means high and minus means low. Okay. That is the meaning of high and low here. So, if you are saying if sig 2 minus 3, then do something else, wait. Okay. So, this means that channel number 2 is high because it is plus there, nothing means plus, and channel number 3 is low, which means there is minus. So, for example, if a part is coming from somewhere, the robot is waiting and seeing whether channel number 2 becomes high and channel number 3 becomes low, then it will go and pick up the part, else it will continue to wait. Okay. So, this is just an example. Another example is wait signal minus 1 2. This basically means wait until signal on channel number 1 becomes minus and channel number 2 becomes plus. Okay. So, this is the basic syntax of the signal command. Then we have reset, which turns off all external signals. We can make particular signals on or off by simply saying on say channel number 2 on, we can make it off, we can reset. Okay. So, at the lowest level we can control the program. Control the program means move between lines, go to some subroutine, come back, and we can communicate with other machines by simply using this on off kind of signals on a particular channel number. So, a robot would be having a large number of channels. It will probably have about 12 channels, and each of the channels can be fitted onto different machines. Okay. For example, a lathe machine, a conveyor, AGV, and there would be some kind of logic in the program which will indicate that a particular task has been done or not done. Now, so this is at the lowest level. Okay. So, this is very simple. This is the simple way of communication. Now, if you are using other sensors, for example, if you are using force sensors or torque sensors, or we are using light curtains or lasers measuring some distance, then this information is not essentially high and low. Okay. So, that is a continuous information, and this continuous information essentially comes from analog signals. So, this is my analog signal. So, let us say force, distance, then torque. Okay. These are all analog signals in the real world, and the robot controller cannot understand analog signals because it is basically a digital controller. So, this analog signals have to be converted into digital, and this conversion is done by some kind of a data acquisition system or an analog to digital converter. So, that is my analog to digital, where the force sensor will be sampled and it will be converted to a digital signal and then given to the computer or the robot controller to understand. Now, the other type of signal can also be digital. For example, an encoder reading is directly digital. So, in this case it does not need to convert because it is already getting a digital reading. So, these are some of the input signals which are coming from the real world: analog signals, then we have digital signals, then we have counters. Now, if the robot is performing a task, how many times it has performed the task, it has to keep a record of, okay, because the robot will have to perform a very large number of times. Okay. So, each time it is performing the task, it is updating the counter, and basically it is storing how many times it has done the task. So, there are counters. Again, there are sensors. Now, sensors are there, internal sensors are there in the robot itself, for example, measuring temperature. When the robot is operating, it is measuring the temperature of the controller, which is happening, the motors. So, temperature of motors, okay, sensors, because if the motors become too hot, then there is chance they can burn. They are measuring the currents of motors. So, internal sensors are there in the robot itself, which are internally monitoring the performance of the robot in terms of temperature, then in terms of the currents that the motor is taking. Now, so all this information, analog sensory information, digital, then counters, sensors, are passed through this data acquisition hardware, or which consists of ADCs and DSCs and signal conditioning, and then it is passed on to the computer for performing the program. Okay. So, we will not go into the very details of this, but it basically means that analog signal. So, some of the sensors we have seen give us analog signals, and the analog signal is essentially a continuous signal that can be of any value, okay. And analog signals include voltage, they include temperature, pressure, sound, load, etc., etc. Now, the robot cannot basically understand this, so it has to use an analog to digital converter, convert to digital form, and then understand it. These are some examples of an analog signal. We have a continuous signal, which is so this signal is a continuous signal in the real world. Now, digital signals are they are sampled. So, analog signals are sampled, and then they have values only at certain instance of time at which they are being sampled. Okay. So, a digital signal will look say, for example, analog signal is being sampled. So, it is going to have values only at particular instance of time. So, it will have the analog signal is being converted to digital, and then it is being given to the computer. Now, ADCs convert analog to digital to signals, DSCs convert digital to analog signals, and robot use ADCs to convert force, distance from analog to digital values. So, the robot would be having analog to ADCs and DSCs in particular channels. Okay. Now, these are some of the other sensory syntax that are used. So, this is my syntax of the commands. It basically says ADC and DSC. So, ADC 1 means ADC in channel number 1. So, this is my channel number, and ADC 1 means the whatever input analog signal is coming on channel number 1 is being converted to digital and then being given somewhere. DSC 1 means convert the signal on channel number 1 from digital to analog values. For example, a statement here is var 1, which is a variable 1. So, this is a variable which is the name of a variable. Variable 1 is equal to ADC 1. So, whatever signal input is coming on channel 1 on the ADC will be converted to digital and then will be given there. Okay. So, suppose this is a force sensor, then whatever force is coming on channel number 1 will be converted to digital value, and it will be assigned to variable number 1. Okay. So, for example, if this is if the objective is to monitor force, then this variable 1 will be the force which is coming on channel number 1. The other syntax that are used are sine, cos, then square root, not equal, not equal, greater than, which are basically computer operations. Okay. The other aspect that we are looking at is the lead through programming. So, today we will stop here with the basic syntax. So, this is basically the syntax for writing a program. Writing a program in VAL II. Okay. Now, the other way is lead through teaching, and then we will look at some examples of how to program. So, this today's class we covered the syntax, and next class we will be covering the actual writing of the program and how to write a program for running a robot. So, today we will stop here. Thank you.